In this video, we're going to be talking about sort of the opposite of fission, which is fusion. So nuclear fusion is when two very small nuclei are combined to form a larger, one or more larger nuclei. So we're combining two small nuclei into a larger one. So this is what's happening inside the sun and other stars. So this one does occur naturally, but not on Earth. This is what generates the heat and light that we get from our sun that allows us to live on planet Earth. So good thing for fusion, we like fusion. And is just how stars function. So a few examples of most of what is going on in stars is fusion of various isotopes of hydrogen. So for instance, we could combine an isotope, a nucleus rather, of hydrogen 1 and a nucleus of hydrogen 2, and that gets us a nucleus of helium 3. There are all sorts of different things that can happen. This fusion process can continue. That helium 3 could combine with another helium 3 to create a helium 4 and a couple of protons, aka hydrogen 1. So in this one we end up with a couple different products. Some of them are actually smaller than what we started with, but as long as at least one of the product nuclei is larger than anything you started with, it is considered a nuclear fusion process. Those two protons can combine to form hydrogen 2 and emit positron. There are all sorts of different types of things that can happen in nuclear fusion. So again, it's kind of complicated, hard to predict exactly what's going to happen, but they always have this common theme of smaller nuclei combining into larger ones in some way, shape, or form. So again, these are just a few examples of what can happen and are some of the most common types of reactions that are happening inside stars. Stars are mostly made of hydrogen and helium. The smallest elements are the ones that are kind of easiest to do fusion. The larger you get, the more difficult it is to get a nucleus to be involved in a fusion process. And there's actually a hard cutoff at iron. Nothing larger than iron is capable of undergoing fusion at all. And as you get closer and closer to that, it gets much, much more difficult. So hydrogen and helium are by far the most common things that react in these types of processes, most often to produce other isotopes of hydrogen and helium. Once you kind of get as big as you can within those elements, they do start creating heavier elements as well. And you may know that stars have a life cycle that after a while a star does die, and that is when essentially too much of it has turned into iron, that the star no longer has enough material available to sustain the fusion process. And that is when stars eventually go out. So as a star kind of moves through its life cycle, is because the types of fuel that are available are changing, that it's running out of smaller things and starting to produce larger atoms. So the properties of the star start to change over time because the chemistry that's happening inside is changing. So as you might expect, given that these are happening literally in the sun, these reactions take place at extremely high temperatures generally. So there has been a lot of research into the potential of using nuclear fusion as a power source. We talked in the last video about how the nuclear power plants that we have today are all based off of nuclear fission. Because that's what we are most easily able to actually do and accomplish. Because of the temperatures required for nuclear fusion, in order for it to work, those extremely high temperatures are necessary. Surface of the sun level temperatures are necessary. And that is really hard to contain. There is no material known to man that can contain that level of temperature. So doing nuclear fusion is actually very difficult. There has been a lot of research into what's known as cold fusion, performing fusion at lower temperatures or finding ways to actually contain it, and there has been some success. It's not something that's being employed currently, but it's a really interesting idea. So fusion, as you can tell from our sun, produces lots of energy. It gives off heat, it gives off light. So we could potentially harness that, if we're able to be a power source. So the good things about this if we could get fusion to work, is that the fuel is readily available, is essentially unlimited. Hydrogen especially is pretty abundant. So fuel is readily available. Pollution is also not a big issue with this. With nuclear fission that we were discussing yesterday, the byproducts of nuclear fission are often extremely dangerous, highly radioactive nuclei with really, really long half-lives. So we end up with this nuclear waste that we have to put somewhere for literally millions of years in some cases until it's actually going to be safe. But with fusion, the only major radioactive byproduct is hydrogen-3. Also known as tritium, which is a beta emitter, so not super dangerous, like not great, but not super dangerous, with a fairly short half-life of only around 12 years. Double check that number. Yeah, around 12 years. So that's much, much shorter in terms of half-life than most of the products of fission, which means that within a century or so, it's not really going to be a hazard anymore. So pollution is not a huge issue with fusion, so that's pretty cool. But again, the problem, I guess it's not really a problem, but what's holding us back is those high temperatures, is that it's just really, really hard to do. And we haven't actually worked out how to do this on Earth yet. So some progress has been made. It's a really cool idea that a lot of people would like to see come to fruition, but we're not there quite yet. So there are potential benefits if we can make it work. These days we have lots of other alternative power sources as well. Solar and wind and all of those things are definitely improving our environmental footprint compared to using coal-powered power plants and fission-based nuclear power plants that have a lot of waste disposal issues as well. The only actual application of fusion that has been seen on Earth thus far is once again in war, nuclear weapons, specifically the hydrogen bomb. So we mentioned yesterday that the atomic bomb or the atom bomb is a fission-based explosive where the chain reaction is just not controlled. We let it blow up. In the case of a hydrogen bomb, this is a fusion-based bomb, but really it's kind of a two-for-one deal, because in order to generate the temperatures needed for fusion to occur, we need to do nuclear fission first. So in order to generate the necessary temperature, for fusion, fission reaction occurs first. Which initiates fusion in the fuel for the fusion portion is what's known as lithium deuteride. Deuterium is just a common name for hydrogen 2. For whatever reason, we gave cute names to all of the isotopes of hydrogen. Hydrogen 1 is known as protium, hydrogen 2 is known as deuterium, and hydrogen 3 is known as tritium. So lithium deuteride is the typical fuel that was used in hydrogen bombs. So both lithium and deuterium are really small nuclei, so they are both able to undergo fusion pretty readily. So we set off the fission part first, and that gets really, really hot with all of the energy that it releases, and it gets hot enough that it initiates the fusion of the lithium deuteride, which generates even more energy. So these types of weapons have the potential to give off massive amounts of energy because you're doing both of these types of nuclear reactions at once.